Okay, so let's do one more example for first law of thermodynamics for a control volume. Here we have a steam turbine. You can see it's a diverging duct, and really hot steam goes into the turbine at surface number one. And then what's inside the steam turbine is you have this blades on the shaft. They can rotate. So the very hot steam will hit the blades and make them turn. And then the hot steam will cool down and it comes out of surface number two. So what happens here is really hot steam cools down, converts the heat into the mechanical rotation of the blades, which then will be converted into electricity, for example, to power up your house. This is one example for conversion from heat to mechanical work, just like the engine in your car. Okay, what we have is T1 is given 400 Celsius, P1 is given 60 bar, very high, mass flow rate is given 4,600 kilogram per hour, V1 velocity V1 is 10 meter per second, and then at surface number 2, we know point 2, we know P2 will be zero point 0.1 bar, much lower. Quality X2 is equal to zero point 0.9, that means at number 2, it's a mixture. It's water mixture. It's not F or G or superheated, but a mixture. V2 is equal to 30 meter per second, and W dot CV, the power generated by the blades, is 1000 kilowatts. W dot CV, like we said before, comes from moving parts. And in this example, you do have moving parts, which are the blades. They're rotating. Okay, so W dot CV for this problem is not equal to 0. What we're looking for is first one, sketch the process on P versus nu and a T versus nu diagram. Second one is to to find heat transfer rate Q dot. Okay, let's start from part one, the two diagrams. Okay, so we always sketch the vapor dumps first. And then, just like before, on the P versus nu diagram, we have constant temperature lines. How to sketch constant temperature lines? Curve down, straight, and curve down. And we'll sketch one more. One for T1, the other one for T2. And then on T versus nu diagram, we sketch constant pressure lines. Curve up, straight, curve up, straight, and curve up. Okay, so now let's go back. P versus nu diagram. Which one is T1? Which one is T2? T1 is 400 Celsius. What's going to happen to T2? T2 is not given, but we know hot steam goes in and it's gonna push the blades, make them turn. What comes out of it is the cool down steam. So T1 to T2, which one is higher? T1 must be higher. T2 must be lower because this is a cooling down process. So the top one should be T1 and the bottom one should be T2. Next one, if we go to the T versus nu diagram, which line should be P1, which one should be P2? P1 is given 60 bar and P2 is given 0.1 bar, so obviously P1 is higher, so the top one should be P1, bottom one should be P2, just like before. Okay, so next we need to locate point number 1. Okay, so we know on the P versus nu diagram, let's locate point number 1. Number 1 must be on T1 line. Okay, and then where on this T1 line, essentially you're asking yourself, what is the phase of point number 1? What is the phase of number 1? How do we do that? Same as before, we can find out the phase from those two numbers, T1 and P1. Remember how to do it? We go to table A3, you start from P1, 60 bar, you look for the corresponding saturated temperature. If your actual temperature is even higher than the saturated temperature, the substance must be at superheated state. Okay, so that's what we will do. Table A3, we start from pressure P1, which is 60 bar. And we find a corresponding saturation temperature, we call it Tsat1 from the table. Let's do it again. Table A3, we start from the pressure, and the pressure for us is 60 bar. So where's 60 bar? 60 bar is right here. First column, 60 bar. Second column is the saturated temperature is 275.6. Unit is Celsius. Okay, go back to our notes, and we can write it down. The saturated temperature at number 1 is 275.6 Celsius, and my actual temperature T1 is 400 Celsius. And obviously my actual temperature is even higher than the saturated temperature. So our conclusion is point 1 must be superheated. Okay, so for example, I can put number 1 here, and correspondingly, I can put number 1 here on a T versus nu diagram, because it must be on P1 line, and then we know it's superheated, so it must be to the right side of the vapor dome. Okay, so we're done with number 1. Next, we need to locate number 2. We need to locate number 2. Okay, so we know on the P versus nu diagram, it must be on T2 line, but do we know the phase? Actually, we do. Actually, we do. Why? Because quality is given. Quality is 0.9, so that means it must be a mixture. Point 2 must be a mixture, so point 2 must be within the dome. So can I actually put point number 2 here? Does it satisfy requirement that T2 point 2 has a temperature T2? Yes, because it's on T2 line. Next, does it satisfy the second requirement that T2 must be a mixture? Yes, it does. But if that's the case, when you connect 1, 2, it's going to be to the left. Second option, can number 2 be here directly below number 1? And if that's the case, 1 to 2 will be vertical. And third option, can number 2 be here? To the right. All three possible locations of number 2 satisfy the two requirements. First one, temperature is T2. Second one, a mixture within the dome. So which one will be the correct? How do we decide? First case, to the left. Second case, vertical. Third case, to the right. So which one is right? Which is the correct one? How? We do the same thing as what we did in the last example. You need to compare the two x coordinates. If the two x coordinates for number 1, number 2 are the same, it must be a vertical line. If the x coordinate is bigger, then it goes to the right. If the x coordinate becomes smaller, then it goes to the left. So we need to compare the two coordinates, which are nu1 and nu2. Okay, how do we look for nu1? We know point number 1 is superheated, so we must go to table A4. To use table A4, you have to have two inputs. The first input is, we know P1 is 60 bar. The second input we know is T1, 400 Celsius. And from here, we can easily find nu1. Okay, let's go to table A4 this time. And the pressure we have is 60 bar. Okay, very high. Where's 60 bar? Okay, here, this is table A4 at 60 bar. And then the second input we have is temperature. Temperature is 400 Celsius, right here. So let's continue. 400 Celsius. This is everything at 400 Celsius. And the one we're looking for is nu1. So the nu1 very easily can be found, must be 0.04739. And like I said before, I also suggest you write down as many properties as you can, so to avoid coming back to the same table. The second property I'm going to write down for now is H, 3177.2. And do not forget the units. Okay, do not forget the units. All right, so now let's go back to the table and write down what we found from the table. We found nu1 0.04739 meter cubic per kilogram. We also found H1 3177.2 kilojoule per kilogram. Okay, so now we're done with nu1. What's next? We need to find nu2 and compare nu2 with nu1. How do we look for nu2? Remember, well, the first step you do is always to identify the phase. And we know point 2 is a mixture. How do we look for nu if you have a mixture? We derived the equation before. Do you remember how to write down this equation? Nu2, because point 2 is a mixture, so we have two components. They are nu2F and nu2G. Saturated liquid F and saturated vapor G. Okay, and then how much vapor do we have? That's the definition of quality. And then how much liquid do we have? That's the rest. So 1 minus x2. Do not forget to give quality x a subscript, x2. Okay, so now do we have x2? Yes. In order for us to find nu2, we just need to find nu2F and nu2G. Okay, what do we know about point number 2? We know P2. P2 is 1 bar, 0.1 bar. So if we start pressure, you have to go to table A3. Table A3, pressure we know is 0.1 bar. And from the table, you can easily find nu F. In our case, we call it nu2F. And nu G. In our case, we call it nu2G. Okay, so let's do that. We go to the table A3. And we know pressure is 0.1 bar. 0.1 bar is in this row. This is 0.1 bar. And we're looking for nu F and nu G. Nu F is right here, 1.0102, and do not forget, multiply by what? 10 to negative 3. Okay, every number in this column has been magnified by 1000 times. So if you look for the true value, you have to go back by dividing by 1000. And the nu G, very easy, 14.674. Okay, and like I said, I also recommend you write down as many other properties as possible. So what I'm going to write down is HF 191.83 and HG 2584.7. And do not forget the units. Okay, again, just be careful. This column HFG is not HG. HFG is HG minus HF. All right, so now let's go back to our notes and write down those numbers. Nu2F 1.0102 times 10 to negative 3. And do not forget the unit. Nu2G 14.674 meter cubic per kilogram. And then, like I said, I also looked for HF and HG. In this case, H2F, H2G corresponding at P2. First one, 191.83 kilojoule per kilogram. Second one is 2584.7 kilojoule per kilogram. And again, just like before, I make a note here so you don't forget. Multiply by 10 to negative 3. Okay, so now we can easily find nu2. Okay, plug and chug. This is the equation for nu2. We have everything. 1 minus 0.9 times nu2F plus 0.9 times nu2G. Everything is in SI unit, so solution for nu2 is 13.206 SI unit meter cubic per kilogram. So now I have nu2. Alright, so let's take a look. This is nu1, 0.04739. This is nu2, 13.206. Which one's bigger? Obviously, nu2 is bigger. So what is our conclusion? 1, 2, 2 must be to the right. Nu2 greater than nu1, that means the x-coordinate becomes bigger. If the x-coordinate becomes bigger, this line must be to the right. Okay. So out of the 3 possible solutions, there's only one that is correct. The one is to the right. Okay, so let's remove those points. Okay, so number 2 must be somewhere here. You can draw a dash line, vertical dash line. So number 2 must be to the right of the dash line. And must be within the dome because of the mixture, and also on T2 line because the temperature is T2, and then you can finally connect 1 and 2. 1 to 2 must be skewed to the right. Okay, so that's P versus nu diagram. What about T versus nu diagram? Very similar. We've located number 1 already, so next one is number 2. How do we locate number 2? Do the same thing. Draw the vertical line, and we know number 2 must be a mixture, so within the dome. And next, we know nu 2 is bigger than nu 1, so number 2 must be to the right of number 1. And then you can connect 1 and 2. Must be skewed to the right, and number 2 must be on T2 line because the pressure of number 2 is P2, and also number 2 must be within the dome because it is a mixture. So this is how you sketch the two diagrams. Okay, and then the last question is to look for heat transfer rate Q dot. Okay, which equation has Q dot? We only have one, first law. Okay, but remember at this moment, if you ever use first law, the first thing you have to do is to identify if your system is a closed system or a control volume, and then choose the corresponding equation for each one. In our case, it's a control volume because you have mass transfer, so we have to use the long version of first law. Q dot minus W dot CV and then plus, do you remember, sigma M dot I? Because there's only one inlet, so I don't need to write sigma anymore. So just write M dot, and I don't even need to give the mass flow rate a subscript. Why? Because the problem said it's at steady state. Oh, not, so let's add it, steady state. At steady state. So mass flow rate never changes. Mass flow rate does not need a subscript. Okay, plus h1 plus 1 over 2 v1 squared plus gz1 because number 1 is inlet minus m dot exit h2 plus 1 over 2 v2 squared plus gz2. There's no need to use sigma again because there's only one outlet. Right hand side dE over dt. Same as before, this term goes to 0 because it is at steady state. And then what else can we do? We're looking for Q dot, so that's okay. We do have W dot CV, that's good. And then mass flow rate given, very good. And H1, did we find H1 before? Oh yes, H1 is right here. We did find H1, so that's great. And V1 is given. Okay, and H2, we don't have H2. V2, what about V2? V2 is V2 given? Yes, V2 is given, 30 meter per second. V1 is 10 meter per second. So both V1 and V2 are given. Very good. And then what about GZ1, GZ2? What essentially you're doing here is M dot GZ1, M dot GZ1, and then minus M dot GZ2. What's the relation between Z1 and Z2? Does the height change? The height does not change, just like the previous example. The height does not change, so GZ1 will cancel out GZ2. Okay, so this equation becomes Q dot equal to, because Q dot is the only one we're looking for, Q dot is equal to W dot CV minus M dot multiplied by H1 minus H2 plus V1 squared minus V2 squared over 2. Okay, so that is the equation. All right, we have W dot CV. We have mass flow rate, we have H1, we don't have H2, we have V1, we have V2. So if we ever want to find heat transfer rate Q dot, we just need to find H2 first. How do we look for H2? And remember, when you look for a property, the first thing you need to do is to find out what's the phase. And then based on the phase, you make a plan. What is the phase of number 2? We said before, number 2 is a mixture. How do you look for specific enthalpy H for a mixture? We derived the equation earlier before. Just like specific volume, you have two components. They are point F and point G. So you have two components, H2F and H2G, one for saturated liquid, one for saturated vapor. plus. And then how much vapor do you have? That's the definition of quality, x2. And then how much liquid do you have? That's the rest, 1 minus x2. Okay, so now let's take a look. Do we have x2? 0.9 given. Do we have H2F, H2G? Yes, I found those two earlier from the table. They are right here. Okay, so now I just do plug and chug and I can find H2 easily. Okay, solution for H2 is 2345.4 kilojoule per kilogram. The unit is kilojoule. Why? Because the unit for those H2F and H2G is kilojoule per kilogram. So we keep the unit. Okay, so now I have everything on the right hand side to look for a heat transfer rate. Q dot equal to W dot CV minus M dot H1 minus H2 plus V1 squared minus V2 squared over 2. We have everything in the right hand side. Plug and chug. And be careful here. Why? Because you have so many different properties in the right hand side. So what I suggest you do is to convert everything to SI. So first of all, what is W dot CV? W dot CV is 1000. And what is the unit? 1000 kilowatts. So we need to convert kilowatts to watts by multiplying 1000. Minus, what is mass flow rate? Mass flow rate is 4,600 kilogram per hour. Kilogram is SI, but hour is not SI. Per hour, I need to convert per hour to second. So divided by 3,600 seconds. So now it becomes kilogram per second after this conversion. And then H1 is 3,177.2 kilojoule per kilogram. So multiply by 1,000 to convert kilojoule to joule. Minus H2. I just found H2. 2345.4 times 10 to third because we want to convert kilojoule to joule. We need to have SI unit. Okay, plus V1 squared. V1 is 10 meter per second SI unit. Minus V1 squared minus V2 squared. V2 is 30 meter per second SI unit. Okay, so now everything is in SI unit. Solution negative 62300. And what should be the unit for Q dot? Must be SI. What is the SI unit for heat transfer rate? It's watts. And then we do one more step to convert it to kilowatts. Negative 62.3 kilowatts. And your solution is negative. What does that tell you? If the heat transfer is negative, that means the system loses heat. If the heat transfer is positive, that means the system gains heat. In this case, the system loses heat.